So the last piece of the puzzle here is to show how to implement custom non-concurrent collectors. And it may come as no surprise that we're going to show the use of the factory method on collector in order to implement our custom non-concurrent collector. So hopefully this will kind of bring it all together full circle, and you'll see the richness of these interfaces and how they work under the hood. So we're going to apply these capabilities, especially the factory method on collector, to a couple of parts of our SimpleSearchStream program. And if you go back and look at some of the earlier discussions of the SimpleSearchStream program, you'll see a bunch of places where I would mention obliquely that there was a downstream collector created and so on and so forth. Or I would say, here's how we format the output to look nice. And I didn't say a whole lot at the time because I was building up suspense for later discussions. So now we're finally going to resolve that suspense. We're going to go take a look at how the method in collector is used to create these custom collectors. The first example, we'll use collector to implement the toString method on the search results class. And so we're going to see how collector can help make that work. And this is the 5-parameter version of collector which, interestingly enough, only has 4 parameters, but we'll talk about that in a second. So if you take a look at the searchresults.java file, you'll see that there's a class called searchresults, of course, and it's got a toString method. And that toString method is used whenever we want to get a nice, humanly readable representation of the indices where the search results occurred during the SimpleSearchStream program. So again, just to go back to the use case and the requirements there, we wanted to print out all the index locations where given words appeared in the input. So Ray appears at certain places. Doe appears at certain places. Me appears at certain places. And so this is the method that creates a string that indicates where the indices are in the context of that string, the input that we were searching. So let's take a look at how toString works. There's a bunch of things that are part of it, but here's the part that's interesting. We take the list of result objects, which of course, if you recall, our splitterator was created in the search for word part of the program. And that then returns a list of result objects. And we want to turn that list of result objects into a string that will contain all the indices where each of the results occurred with a vertical bar used to separate each index. So we want to basically create a string that has vertical bar separators between each of the indices. And to do this, to make it really simple, we're going to use the collector method. And this is the 5-parameter version, but because there are no characteristics that we're setting, then we ignore the characteristics parameter. And that's an optional parameter, so you don't have to provide it. So we actually pass 4 parameters into the 5-parameter version of. That may seem a little contradictory at first, but believe me, when we see the 4-parameter version of in just a moment for a different custom example, you'll see how we only pass 3 parameters to that one, because in both cases, we're ignoring the characteristics final parameter. Okay, hopefully that was it was clear as mud. If you have any questions, as always, don't hesitate to ask. So let's take a look at the different parameters that we're passing to this collector factory method. And this is going to be creating a custom collector that's going to make ultimately a string where all the indices will be separated by vertical bar. So the first thing we're going to do, this is the supplier lambda expression, is we're going to make ourselves a lambda expression that will create the mutable result container. And the particular mutable result container we want in this case will be a string joiner. And string joiner is a class that's defined in Java that is going to allow you to concatenate a bunch of strings together. And the string joiner will make sure that between every string you concatenate or you add, it puts a vertical bar between each of them, which is exactly what we want to get the output that we're looking for here. So that's the type of the accumulator, is going to be a string joiner with vertical bar as the parameter to use as the separator. The accumulator is provided by this lambda by consumer, And what we're doing here is we're defining a little piece of anonymous code which will take the current string joiner, which of course will be the one that was created by the mutable result container factor method, and we're going to then go ahead and add a new string to the ever-growing joiner, string joiner. And in this case, of course, there'll be a vertical bar put there magically by the framework. So whenever someone needs to accumulate something, this by consumer will take a joiner, and it'll take basically the result, which is going to be the result object, and it'll go ahead and add that result object to the end of the joiner, and of course, that add method will put the vertical bar in the separator part between those two elements. You can see that we're using a little shorthand here where J comma R is essentially equivalent to string joiner J comma search results dot result R. That's what those are expanding to with Java's type deduction capabilities. The third parameter we pass in here is the combiner, and this is going to be used to take two string joiners and merge them together. So we pass in a method reference called string joiner : merge, and were we to need this, which would only occur if we were doing parallel streams, then we would use the merge method to merge together two string joiners. This is not used for sequential streams, but we have to provide it nonetheless, just in case someone decides to make this a parallel stream. We're all ready to go. And then the final method here, this is actually not a bad example of using a finisher that's not just the underlying accumulator or mutable result container. In particular, you'll notice that the type of the mutable result container was string joiner, but what we want to get back as the result of this is a string, not a string joiner. So therefore, what we do is we use the toString method on string joiner, which goes ahead and takes all the internal data structure that's used to build up this joined string with the vertical bar between each of the sub-elements. And then toString will simply convert that into a final string. So that's a nice example of showing how you can use a finisher that's not just the identity finisher. So that's why we used this 5-parameter version of, because we wanted to be able to take control over the finisher. So as I mentioned before, even though we're using the 5-parameter version, we only pass 4 parameters because characteristics ... signifies it's an optional parameter. We didn't change any characteristics. They're all the same as before. So that's why we could do that. Okay, let's now take a look at another example of implementing a custom non-concurrent collector. And this one is something I also mentioned somewhat obliquely back a number of lessons when we were talking about the word searcher print suffix slice method. And we talked about how we were talking about visualizing it. We could also go look at the implementation part as well. But in either of those lessons, we talked about this method that I didn't talk much about at the time called toDownstream collector. So toDownstream collector is used as part of this mechanism in order to be able to create a collector to collect up the various result lists into a single merged result list. So that's what toDownstream collector does. So it's in the word searcher.java class, that's where it actually gets used. So we use it to create a downstream collector that merges all the result lists together. And this is just a way to make it more clean and easy to work with. Here's how it works under the hood. We use the 4-parameter version of collector of, once again, only passing in 3 parameters because the last one is optional, which we don't use. It's the characteristics as usual. And here are the 3 parameters we pass to of. We first pass ArrayList : new, which is the constructor reference that's used to make the mutable result container. In case we're going to make it an array list. It's very common, as you can see. We then define the accumulator, which in this case is a lambda expression. And you can see what it does is it's going to take the results list and it'll take a search result object and it'll take the result list and it'll go ahead and add the result list from the search result object to the end of the ever-growing result list. So this way we're kind of concatenating, if you will, the result lists together to make a single result list, which of course is an array list. And we could have used linked list here, but array list works perfectly well. And then the final parameter that we pass in here is a lambda. This is basically a lambda that's used as a binary operator. This is going to be used to merge two result lists together into a single result list. It should look very similar because it looks like all the list merging combiners that we've looked at before. Keep in mind, again, this is not used for this example. It would just be used if we had a parallel stream use case for this particular collector. And again, because we don't need to change any of the characteristics, we only pass in 3 parameters. So that's essentially how the toDownstream collector can be implemented to make a custom collector. One of the things you'll notice so far is I've used the of method in order to be able to make myself these custom collectors. And that'll work for all the cases that are simple, like the ones we've looked at here, where you've got very simple method references or very simple lambda expressions. If you have very complicated lambda expressions, then you're probably better off not using the of method, but you're better off actually implementing the collector interface. Now, we're not going to show that right now because these examples don't require it, and it would be overkill to do it that way. Using of is perfectly fine. But later, when we talk about completable futures and we have a much more powerful finisher that actually does a lot of interesting and complex things, we're going to use an implementation called a futures collector that will implement the collector interface. And you'll get a chance to see how that works. And it's really powerful, very open-ended. Once again, Java's frameworks are helping to make your life a lot more open-ended. Keep in mind, going back to some conversations we had in previous lessons, you have ways of customizing splitterators using the splitterator interface. You have ways of customizing collectors by using the collector interface. And these are examples of how you can take the Java Streams framework that comes out of the box and then tailor it to your particular needs. And that's a very, very powerful feature. A lot of times, languages or class libraries won't give you the hooks to customize stuff, so you're kind of stuck with what you get out of the box. But one of the great things about Java and the Java Streams framework is you can tailor it as you see fit to meet your particular needs. If you'd like to learn even more about implementing custom collectors, there's a video by my friend and colleague Angelika Longer, and she talks at length about reduce versus collect and shows a bunch of other very interesting examples of implementing custom collectors to do all kinds of cool things. So I think it's a couple hours long. So it's a long discussion, longer than we went into here. But if you're really curious to learn more, please go ahead and take a look at this link. It's very informative, and I learned a lot from it. I'm sure that you will too. So that wraps up our coverage of our initial coverage of collectors, focusing here on non-concurrent collectors for sequential streams. Later, once we're deep in the midst of our coverage of parallel streams, we'll revisit collectors, and I'll talk about how non-concurrent collectors work for parallel streams, and then we'll also talk about how you can make concurrent collectors for parallel streams. And people who are doing the grad student version of the assignment will end up implementing the concurrent collector